Hello and welcome to this revision session for GCSE Combined Science Paper 2. So in today's revision session, what we're going to be doing is looking at how to answer examination questions for GCSE Combined Science Physics Paper 2. So if we've been successful and we've learned in this revision session, we should be able to answer GCSE Combined Science Physics examination style questions. We should be able to assess our understanding on our topics for GCSE Combined Science Physics and understand what topics we need to improve upon for GCSE Combined Science Physics Paper 2. So how should you be preparing for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out, whilst on the right hand side write down any pieces of information which you find useful or any hints and tips on answering the questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's now have a look at some questions on GCSE Combined Science Physics Paper 2. So let's start off by looking at the topic of forces. So this question says, a student tested some springs to find the limit of proportionality of the springs. The student had several identical springs and figure 2 shows the equipment used. Plan an investigation to determine an accurate value for the limit of proportionality of the springs. So pause the video now, then unpause the video when you want to go through your answer. Right, when you try to answer this question, you need to write up this method. So what you need to do is you need to write down what you're going to be measuring and with what devices you're going to be using. You need to write down a short, brief method of what you're going to do to get your results, and then finally what you're going to do with the results and how you'll work out the values. So the first thing to do is measure the original length of the spring with a meter ruler. You'll then need to add masses of 100 grams each time. Again, to be fair, you could use 50 grams or 200 grams, as long as it's a consistent value used each time. You can then use this to calculate the force applied to the spring by doing the weight, which is the force, equals mass in kilograms times by the gravitational field strength, which is 9.81. You would then remove the mass and then measure the length of the spring again. If it's still elastic, it should then have the same original length again. Keep on repeating it for different masses, so 100 grams, 200 grams, 300 grams, 400 grams, etc. Continue until the unloaded spring is no longer the original length. It's in fact been permanently deformed, and then the limit of proportionality is where is between the last two forces, where you're still getting that original length. The other way you could do it is that you could then do that experiment, but then plot a graph of force against extension. You would then draw your line of best fit in for your data, and then you notice that the limit of proportionality is where the graph stops being a straight line and starts to curve. So you may wish to do it like so. Now the next question says, a different spring has an extension of 0.15 meters when a force of 120 newtons is applied to the spring. Calculate the spring constant of this spring. So pause the video now, then unpause the video when you want to go through your answer. Right, so in answering this question, you've got to use your equation sheet, and the equation sheet will tell you that force is equal to spring constant times by extension. Now again, it's suggested you pop in the numbers first, you then rearrange. So you write 120 equals k times by 0.15, so k equals 120 over 0.15, so it equals 800 newtons per meter. Again, you should see here, you've clearly set out by popping the values in, then rearranging, then working out your final answer. The next question says, figure 11 shows a rhinoceros running. The initial kinetic energy of the rhinoceros is 72,000 joules. The rhinoceros accelerates for a time of 4 seconds, and the kinetic energy increases to 392,000 joules. The rhinoceros has a mass of 4,000 kilograms. Calculate the acceleration of the rhinoceros. So pause the video now, then unpause the video when you want to go through your answer. Right, with this question, your first notice that's worth 5 marks. So this indicates to us we'll need to use multiple equations. Now there's a couple of ways in which you could do this. The first way is by saying, well, kinetic energy is equal to half mv squared. So you've got your kinetic energy, okay, at the end. So you know that at the end it's 392,000 joules. So you can say 392,000 equals a half times by its mass, which is 4,000 times by v squared. So therefore v is going to be equal equal to the square root of 392,000 times by 2 over 4,000, which is 14 meters per second. So now we know that that's going to be the speed at the end. We can then work out the speed at the start by doing the initial kinetic energy, 72,000 equals a half times by 4,000 times by v squared. So v is equal to the square root of 72,000 times by 2 over 4,000, which is 6 meters per second. We then know acceleration is the change in velocity, so it's 14 minus 6 divided by the time, which we know to be 4 seconds, so we get our answer of 2 meters per second squared. The next question says, Figure 12 shows two of the forces act on the rhinoceros as it starts moving. Determine the resultant of these two forces. To gain full marks, you must draw an arrow on figure 12 to show the resultant force. So pause the video now, then unpause the video when you want to go through your answer. Well, in these types of questions, it's extremely important that you can be able to determine in which direction the resultant force will act. Now you'll notice this isn't actually a scale diagram because the arrows are not going head to tail, head to tail, head to tail. So what I would suggest you do is you make it head to tail by taking the 60,000 Newton arrow and then transposing it so it starts at the top where the point of the 50,000 Newton line is going to be at. So we can then pop it across, and we then say the resultant is from the start to the finish, so it'll be a diagonal line across like so. Then what you can do is, because you've got to do it via the scale drawing, okay, you could then work it through by then working out what the scale is. So you can work out what the scale is. You can see it's going to be 1 centimeter is 5,000 newtons from the length of the other two given from the values. So you get your ruler, you can then measure the length, convert that then into what the value is going to be. So there's 15.6 centimeter line. Okay, each centimeter is 5,000 newtons, so it's 15.6 times by 5,000 is 78,000 newtons. You can then get your protractor, you can then measure the angle to be 40 degrees to the horizontal, and then you can work it through like so. You might say, can you also do it by trigonometry? Well, you can as well. So you could do Pythagoras to work out the size of the resultant force. So you could do you can see your values of 60,000 squared plus 50,000 squared, all square rooted. Then you could use your trigonometry by doing SOHCAHTOA, so tan is equal to opposite over adjacent, and work it through like so. The next question says, figure 13 shows a lunar rover on the moon. The lunar rover obtains data about the moon and transmits this information back to the Earth. Explain why the weight of the rover is less on the moon than it is on the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, well, it's important to note about what the weight is actually measured from, and weight is equal to mass times by the gravitational field strength. Now, the lunar rover doesn't lose mass, so the mass is constant, but the gravitational field strength of the moon is going to be lower than it is on the Earth, so because the gravitational field strength is lower, the weight of the lunar module is also lower. The next question says, figure 10 shows part of a roller coaster. The mass of the train is 44,500 kilograms. The train accelerates along the horizontal section of the track. The average resultant force is 48 kilonewtons. Determine the average acceleration of the train and give your answer to two significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, again, you'll notice that we've got 48 kilonewtons, so we need to convert that into 48,000 because kilo means times 10 to the 3, so it's 48 times 10 to the 3, or 48,000 kilonewtons. We also know we've been given a resultant force and we've got a mass, and we need to work out an acceleration. So the equation from the equation sheet is force equals mass times by acceleration. So you pop in the numbers of 48,000 for the force and 4,500 for the mass, and then you can see acceleration is 48,000 over 4,500, which is 10.666, but then we wanted to do two significant figures, so you start counting your significant figures at the first non-zero number, which is 1 in this case, so it's 1, 0, which is your two significant figures. You look to your third one, it's a 6, so therefore you round up the next value, so it goes to 11. The next question says, at the end of the horizontal section of the track, the velocity of the train is 28 meters per second. The train travels up the curved section of the track and decelerates to a stop. Determine the maximum vertical height that the train could reach, and then explain why the maximum vertical height reached will be lower than the value calculated in 7.2. So pause the video now, then unpause the video when you want to go through your answer. Right, you'll notice that the first question is worth 5 marks. We've got to do a bit of a trick mathematically. So you'll notice that in the first part of the section it's moving, so it's got a kinetic energy, and then the second part is moving up a height, so it'll have a gravitational potential energy. So what we can say is we can say that the kinetic energy lost is equal to the gravitational potential energy gained. So we can work out the kinetic energy by doing a half times by mass times by velocity squared. So a half times by 4,500 times by 28 squared, so it's 1,764,000 joules. That is then the gravitational potential energy. That is then equal to m times by g times by h. So therefore h is equal to the kinetic energy divided by the mass times by the gravity. So you can work that through to therefore be 40 meters. But what's our assumption here? We've assumed that the kinetic energy has turned completely to gravitational potential energy. That will not be the case. Because it's moving along the ground, there'll be some work done against friction or air resistance. So it's not all of the kinetic energy will transfer to gravitational potential energy. So some energy will be dissipated to the internal energy store of the surroundings. Let's now have a look at some questions regarding waves. So the first question says the rover landed on the side of the moon that is always facing away from the Earth. Figure 14 shows the Earth, the moon and a relay satellite. The relay satellite receives microwave signals from the rover and transmits them to the Earth. Calculate the time it takes for the microwave signal to travel from the moon to the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, this is a wave question, but you'll also be aware that you can use the equation of speed is equal to distance over time. Now it tells you that the speed of the microwave is 3 times 10 to the 8 meters. We know that the distance from the Earth to the relay satellite and then from the moon to the relay satellite, okay, is going to be the two values added together. So it's going to be 520,000 kilometers, which we can then convert into meters by saying it's 520 thousand there, so 520 million meters. So we can say 3 times 10 to the 8 is equal to 520 million meters over the time. We can then rearrange the equation and make time the subject. So therefore time is equal to 520 million over 3 times 10 to the 8. So we get 1.73 seconds. Again, just make sure you write out your full equation, you pop in the values, you then rearrange it, you then write in your answer and check to see if it looks sensible. And 1.7 seconds looks a sensible time for this signal to take place. The next question says the microwave signals transmitted to the rover have a frequency of 12 gigahertz. Calculate the wavelength of the microwaves. So pause the video now, then unpause the video when you want to go through your answer. Right, you should also be aware that the equation for a wave speed is equal to frequency times by wavelength. Now we should also note that the frequency is given in gigahertz. So we want to change our gigahertz into hertz. Giga means times 10 to the 9. So therefore 12 gigahertz is 12 times 10 to the 9 or 1.2 times 10 to the 10. So therefore we can pop in our numbers and say it's 3 times 10 to the 8 equals 1.2 times 10 to the 10 times by the wavelength. Therefore rearrange it, wavelength the subject, 3 times 10 to the 8 over 1.2 times 10 to 10, so it's 0.025 meters. The next question says a student investigated how the angle of refraction varies with the angle of incidence for light entering a rectangular glass block. Table 1 shows the results. So plan an investigation to obtain the results in table 1 and you should include a diagram in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, once again, if you're planning a method, state what you're going to measure and how you're going to measure it, state the method that you're going to use, then state what you'll do in terms of getting your data. So the first thing you note is you'll draw around the glass block, you'll use a protractor to measure an angle of 90 degrees to the glass block, you then draw a normal in at 90 degrees with a dashed line, you'll then measure angles of 15, 30, 45 and 60 using the protractor. Again, we're using those values because that's the values of the angles of incidence in the table. We always measure the angle of incidence from the normal, so you would do it as such from the normal to the line. You then mark the position of those incident rays. You then use a ray box and slit to produce a narrow beam of light and shine the ray of light along the incident ray 15 probably the first one. Draw crosses at the ray that emerges from the block. You then draw in the path coming out of the block and then draw a straight line in as a path going from the path going in and the path going out. Then you can measure the angle of refraction to the normal using a protractor, and that's the angle inside the block, then not the angle outside. You'll do your 15, 30, 45, 60 and 75 angles of incidence. You'll then use your protractor to measure the angles of refraction for those different values. The next question says, figure 6 shows an X-ray image of a broken leg. Give one precaution that should be taken by a hospital worker when using X-rays. Then explain how X-rays are able to produce an image of bones. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to understand the issues that you've got with X-rays. So X-rays are ionizing, so to prevent the X-rays from irradiating you, either use a lead apron or stand behind a lead-lined shield. Now, how do X-ray radiographs work? Well, X-rays cannot pass through solid, dense objects. So the X-rays will be going straight through the tissue and skin and blood of the person, but will be absorbed by the bone. So therefore, your sheet starts as white, and then when the X-ray hits the sheet, it turns black. So anywhere white is where the X-ray is being absorbed by the bone and doesn't change its colour, while the black bit is everything else. The next question says, an X-ray has a frequency of 2.4 times 10 to the 19 Hz. Calculate the wavelength of the X-ray. Then X-rays can also be used to treat cancers. The wavelength of the X-ray used to treat cancers is shorter than the wavelength of X-rays used to produce X-ray images. Explain why. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first question, you've got to use your equation. Wave speed is equal to frequency times by wavelength. So it's 3 times 10 to the 8 equals 2.4 times 10 to the 19 times by the wavelength. Sub in the numbers first. Then rearrange and say it's 3 times 10 to the 8 over 2.4 times 10 to the 19. So we get 1.25 times 10 to the minus 11 meters, which makes sense for an X-ray image. Now the next thing to understand is that you've got to understand the link for wavelength and frequency for electromagnetic waves. The shorter the wavelength for an electromagnetic wave, the higher the frequency, so the more energy delivered per second. So more energy is transferred by the higher frequency, shorter wavelength waves. So therefore, if more energy is being transferred, well therefore the X-rays are more likely to kill the cancer cells than there would be for an X-ray of a longer wavelength. The next topic we're going to look at is now magnetism and electromagnetism. So the first question says, a teacher demonstrated the magnetic field produced around a current carrying wire. Figure 6 shows the equipment the teacher used. Firstly, why does the compass needles in figure 6 all point in the same direction when the switch is open? Then secondly, describe what happens to the compass needles when the switch is closed. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've just got to know that if there's no strong magnetic field near an object, it will follow the Earth's magnetic field. So the compass needles are all lined up in the same direction because they're lining up with the Earth's magnetic field and are pointed towards the Earth's geographic North Pole. Now, the next question, what happens when the compass turns, when the switch is closed? When the switch is closed, the circuit there becomes an electromagnet. The current carrying wire will become an electromagnet, so therefore the circles will form a circular pattern. The compass will form a circular pattern because you get a magnetic field that is of a circle at right angles around the wire. That's what the field line of a current carrying wire looks like. So it'll form a circular pattern. The next question says, the teacher placed the wire between two bar magnets. Figure 7 shows the wire and the magnets. The teacher used Fleming's left-hand rule to determine the direction of the force on the wire due to the magnetic field. Complete the labels in figure 8 to show what each finger represents. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, you've just got to memorize the different parts of Fleming's left-hand rule. So the thumb is the direction of the force or the motion. The first finger is the direction of the field or the magnetic field, if we're more precise. And the second finger is the direction of the electrical current. So you've got to memorize those particular values. The next question says, from looking at the diagram, what is the direction of the force on the wire due to the magnetic field? Then give 2 ways that the teacher could increase the force on the wire due to the magnetic field. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you're going to have to use the left-hand law you've just described. So you're going to have to place your second finger of your left hand pointing upwards to show the current flow. You're going to have to point the first finger of your left hand from the north to the south, from the left-hand side of the magnet to the magnet on the right-hand side. And at that point, you can see that when you're orientated like that, well then your thumb is then pointing inwards into the page, into the screen. So that is the answer. Now for this next question, you should remember that the force on a wire in a magnetic field is equal to BIL, B-I-L. B being the magnetic field strength, I being the current, and L being the length of the wire. Now we can't change the length of the wire really because it's already fixed in place. The two things we can change are how strong the magnetic field is and how much current is flowing through the wire. The next question says figure 9 shows a simple electrical motor. Explain how the coil of wire moves when the switch is closed. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question you've just got to explain what's going on in this coil of wire. So the first thing to note is that the current flow, and you'll see it very clearly labelled on your diagram that they've given you, that from A to B and D and C to D, that the current is flowing in opposite directions. So therefore when current is flowing around the coil of wire in the centre, that the magnetic field produced due to this is going in different directions from A to B and C to D. So therefore the forces that are produced on each side of the coil due to the interaction of its magnetic field with the magnetic field of the permanent magnet is in opposites. So you've got an opposite force on either side of the coil, which will cause our coil to rotate. And that's how a motor will work. The next question says, the teacher demonstrated how the magnetic force on a current carrying conductor in a magnetic field varies with the current. Figure 11 shows some of the equipment used. When is there a current in the conductor, a force acts on the section of the conductor between the magnets. So firstly, describe how Fleming's left-hand rule can be used to determine the direction of the force on a current carrying wire. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, you've just got to memorize what the different fingers and thumbs on your left hand represent in Fleming's left hand rule. So you place your thumb, your first finger and your second finger of your left hand all at right angles to each other, all at 90 degrees to each other. Now your first finger points in the direction of the magnetic field from north to south, the second finger points in the direction of the electrical current from plus to minus, and the thumb shows the direction of motion or the direction of the magnetic force produced in the interaction. The next question says the teacher varied the current through the conductor. The teacher determined the force acting on the conductor using the change in the reading of the balance. Describe how the teacher could use the equipment shown in figure 11 to obtain the results during this demonstration. Include in your answer any additional equipment that the teacher would need, and then give one variable that the teacher should control during the demonstration. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So what you're going to need is you're going to need an electrical circuit as well, because we need to produce that circuit from the previous. If you look at the previous question, we don't have a circuit involved. So what you'll need is as follows. You'll need an ammeter, variable resistor, power supply, switch. You'll then connect them all in series with the conductor. You'll then record the initial reading on the balance. You'll then close the switch, and then that'll produce a magnetic field in the wire. That will then allow your reading to be measured. Now you can then use a variable resistor to change the current, because the size of the current will alter the strength of the magnetic field produced by the wire. So you can record the current on the ammeter, record the new reading on the balance, and then what you can do is to find out what the change in the value of the balance reading was, subtract the initial balance from the new balance reading. What you may wish to do is actually zero the balance beforehand, so you don't have to subtract any value from the start. You would then do different values of current, and it would read off as different values on the balance, and then you can look at the link between the two. Now, as we said before, what does the force of the magnetic force vary on? Well, F equals BIL. So for only looking at how the current I affects the force F, well, the other two factors in the equation have to be kept constant, because they can also affect the value of F. So the magnetic field strength B, or the length of the wire, will also make a difference. Now as well, technically, because we know that the angle angle produced between the field, the magnetic field and the wire will make a difference. So therefore, if the angle of the conductor and the field should be constant as well, because remember, if it's at 0 degrees, you get no force, and if it's at 90 degrees, you get a maximum force. The next question says, figure 12 shows the results. Explain how the results show that the force is directly proportional to the current. So pause the video now, then unpause the video when you want to go through your answer. Right, so if you drew a line of best fit from this data, you'll notice you'll get a straight line of best fit through the origin. Now, the definition of how you can work out direct proportionality from a graph is that it can be shown as a straight line through the origin. So the fact that the line of best fit is a straight line through the origin indicates that they must be in direct proportion. The next question says, the teacher said that this demonstration should be performed using a range of currents as shown in figure 12. Suggests why current values much smaller or much larger should not be used. So pause the video now, then unpause the video when you want to go through your answer. Right, well, you've got to think about why we use those particular values. Now, firstly, we wouldn't use a much smaller value because the current links in direct proportion to the force produced. F equals BIL. So if I goes down, F will go down. So you can see from the values we're getting smaller and smaller values of millinewtons. So if the current went down any further, well then the force detected will be so small it'll be very hard to accurately measure. Remember, in physics, the bigger the value, the more easy it is to measure accurately, because your percentage error, the error you cause, has less of an impact when it's a bigger value. Now, the other issue is why not use a bigger value? Because from what I've just said, well, the bigger the value, the more accurate the result, because the percentage error of your mistakes is a smaller number, so it's a more accurate value. Well, you've also got to consider safety as well. If we increase the current and increase it, well then the conductor will get hotter and hotter and hotter due to the resistance in the wire, so that could cause it to overheat, which is a safety hazard. So always consider the accuracy of your results, but also the safety of which you can carry out your experiment in. So that brings an end to our revision session today on GCSE Combined Science Physics Paper 2. So if we've been successful and we've learnt in this revision session, we should be able to answer GCSE Physics examination style questions, assess our understanding on GCSE Physics, and understand what topics we need to improve upon for GCSE Combined Science Physics. So thank you very much for watching this revision session on GCSE Combined Science Physics Paper 2. Thank you very much and have a lovely day.